I'm Jonathan Burbaum. I'm Program Director at ARPA-E. I wanted to sort of point out something that we noticed when we were going through this room in the dry run, which is that the slides are a little bit fuzzy. So it's helpful if you can move sort of toward the front. I don't think that every seat's going to be taken, but just if you look at this and it seems a little bit out of focus, that's an AV problem we're going to deal with here. We're also behind schedule. And what I've been asked to tell you is that we're going to run for the full 45 minutes for this, but only have a 10-minute instead of a 15-minute break after this. I think we're going to update this schedule as we're going on the fly. And as was mentioned this morning, we're going with a new question and answer thing. There are no room mics. I've got this tablet up here, and we've got 4 technologists on the panel. Hopefully, we'll be able to figure out how to actually take your questions in. It's a little bit of an experiment. We tested it out this morning, but we'll make do with it. Anyway, like I said, my name is Jonathan Burbaum. This panel discussion is technology focusing on the future of fuels. And I've got 3 other panelists up here with me, and I thought I would go through a little bit of an introduction to how ARPA-E has and continues to think about the fuel space in energy innovation. The panel is shown here. I'm a program director in the Petro program. I'm going to go into a little bit here, but to my left is Dr. Ramon Gonzalez, joined us from Rice University, and Dr. Will Regan, an ARPA-E fellow, and Dr. Robert Conrado, an ARPA-E senior fellow, who are going to also be giving presentations on some of the things that are going on in sort of new idea space at ARPA-E. So what the goal of this session is really to provide the community with some insight onto what our processes are in program development, project selection, and funding, and to illustrate how these processes have led to ARPA-E's portfolio. And that's sort of that's sort of the dollar signs here. We're outside where other people fund. We sort of fund in clusters and sometimes not. So that's basically what that's supposed to represent. So this is one of our stock slides, which is the technology acceleration model that ARPA-E uses. We start with an idea or a vision. We run a workshop. The process for program approval. Then the funding opportunity announcement is developed and issued. The proposals are reviewed, rebutted, projects are selected, contract negotiation awards, there's an ongoing technical review, and then the project is handed off to a commercial partner. And in this whole process, in this entire cycle, we gather information and ideas that help us to sort of make it an actual cycle where in this process we learn new things that could be new programs, new concepts, new ideas, new visions, and so forth. And you'll hear some of that today. So one thing that isn't on here is what we did this past year, which I had the I guess privilege of being the chairperson of the Merit Review Board for the open solicitation. So we looked at a very large number of great ideas out there from the community. We're only able to fund a fraction of them, but I have to say I'm proud to be part of the community. It's a great and creative community, and to keep the ideas coming. It's a lot of fun. So I'm going to talk about this sort of backstage here, and Ramon has run a workshop, and he's going to talk to you about some of the ideas that are coming from that workshop. Is currently going through the FOA process, and then our fellows, who are really a source of inspiration for all of us at ARPA-E, are going to show us some of the things, some of the on the edge of the box to outside the box ideas that they've been thinking about. So, focus programs at ARPA-E. We have now focus programs in 2 major areas: transportation and stationary. It's either moving or it's not. And most of our fuels programs are located here in transportation energy technology. There are some programs that have overlap between transportation and stationary, and I could go through all of the acronyms, but I'm not going to burden you with that. I'm going to talk about 2.5 today. I'm going to talk about petro, electrofuels, and then a little bit of heats that came in in the process of generating that actually led to a fuels proposal. It's pretty interesting. So, talk to you first about Petro. This is a program that I've talked about. I think this is for the past. This is my third summit talking in general about this. But we've now taken this all the way through to a publication where we're talking about our ideas of how carbon and sunlight is converted through biofuels, converted into cycle. We looked at, instead of looking at energy, we looked at carbon. And looking at the total carbon absorption potential, you find that the carbon content of not only is the process energy inefficient, it's also carbon inefficient. You don't get much into the product that you want. We set a goal here of doubling the carbon content going into final fuel compared to corn ethanol. So we funded, last year, we started out in 36 million, 36 months, and 10 projects. So these are the performers that you will see in the showcase. The second project is a little bit older. In 2010, there's 56 million for electrofuels. And the idea of electrofuels here is to take out the sort of photochemically inefficient part of the process and instead turn that into reducing equivalents. And you can get reducing equivalents for a variety of sources of electricity, as well as chemical reducing equivalents in hydrogen or hydrogen sulfide. Combine those in a bioreactor with nutrients and water, carbon dioxide, and use the ability of biology to fix carbon to generate advanced biofuels. And this program is going on. In fact, Ramon is managing the project at this point, and we've got a bunch of performers doing good work in that area as well. As I mentioned, we also got fuels ideas from other areas. This is a HEATS program. HEATS stands for high energy or advanced thermal storage. So looking for ways of converting thermal energy into stored energy so that you can store heat. This project had a goal of greater than 10% efficiency at a temperature less than 1500 degrees C, and the process that's going on here is sort of a metal catalyzed oxidation of water to hydrogens and basically to syngas, and there are a couple projects going on in that area. So you see, we have programs that are sort of focused. Some programs that are focused in areas that you might not think, that sort of bleed over into the new areas, and then we have the open solicitation, the open FOA, and I want to talk about that a little bit. As you'll see, a number of the projects, 13 projects out of the 66, could be classified broadly into advanced fuels. And I also put in carbon capture here because there's a sort of a bond between fuel use and carbon emissions that is important to keep in mind. These are the projects that we funded. The main thing to look at here is not to try to read all these titles, but to see that there are some themes that are coming out, and we're going to touch on those themes today. We have you'll see methane in a lot of places, CO2. You also see some things, synthetic gene circuits, partial oxidation of natural gas. So there's a lot of themes that come out of the solicitations that we take in and use that information to help formulate new programs that we might run in the future. I thought I'd give you a quick guide because I know that there will be a lot of people trying to pitch us ideas this week. I hope, this is sort of a condensed version of what's known in DARPA language as the Heilmeier Catechism. It's basically a set of penetrating questions that is designed to elucidate the solution that is coming forward, and is it something that is practical to pursue? So the idea here is to define the practical problem that you're looking to solve crisply for a general audience, and then answer these questions. How are other people doing it today, and what are they running into as their roadblocks? What are you doing that's different than what everybody else is doing, and why now? Why take that approach now? If you're successful, have you really changed the future, and how? How big an impact, and who's going to care about what you're doing? If it is funded, well, how much do you need? if you don't know how much you need, there's a problem. How long is it going to be until there's impact, and what are the risks associated with the project? And how you know when it's off track. You have to measure what you're doing. And these are also the same sorts of questions that we ask when we're establishing a program. Now, it's a way of sort of helping us define relevance in this space. So, with that, I'm going to turn the podium over to Dr. Ramon Gonzalez. I should point out that we have several ways of asking questions here: text, tweet, or actually on the web. There are not going to be any room mics, so it's going to be important that you pull out your iPhones and send us your questions in that way, and then I'll try to figure out how to work this thing. So, Ramon?
Thank you, Jonathan, and good afternoon. I'm going to get my bottle of water here so I don't need to reach for it this way. Is that familiar to you? Like the response from the Republican Party to the State of the Union address, so I guess maybe not all of you saw it. So where do I have the... Okay, so again, my name is Ramon Gonzalez. I am a program director with ARPA-E. I have been with the agency for the last 6-7 months, and today I would like to share with you some thoughts around one of the potential programs that we have been considering over that time. As you can see in the title, it relates to the bioconversion of methane to liquid fuels, basically. So why methane? I think this one's going to be easy. So I think that all of you, if you're in this room, you're familiar with the natural gas, the shale gas revolution, and how much gas we have in U.S. The graph there on the left shows you how the reserves have been growing significantly, and when that happens and the consumption doesn't actually follow that curve, what you end up with is something like what is shown on the right-hand side. That is that the price is really dropping, and more importantly, there is a huge spread there between the price of gasoline and the price of natural gas on the same energy basis. So that is actually a huge opportunity, an opportunity to turn that green light there into gasoline, basically. Now, if you happen to develop technologies that allow you to do that efficiently, you may end up having enough essentially liquid fuels to meet U.S. demand for transportation fuels over the next 50 years, just thinking about the use of natural gas, and that is considering that natural gas will continue to be used for other applications as it happens today. How can we do that? So if you think about commercial technologies that are out there, the ones that can be deployed, the one example is the gas-to-liquid Fischer Tropsch process that is able to take methane, take natural gas, and put it into a liquid fuel that can be used. Now, there's a couple of important points that need to be made about those type of technologies. One of them is that it is a very complex process. The picture there tells you the story, I guess. That is the picture of a facility for the conversion of natural gas to liquids. As you can see, it's huge. So don't think that it's a city. It is a facility that converts natural gas to liquids. So it's very complex. There's a need to go to large scale because of CapEx and other reasons. But the translation of those two combined is that you're going to have a very high capital expense there. Your investment is huge, in the order of $1 billion. Now, why are we thinking in a bioconversion type of process? Because we believe that that type of process could take care of those two issues there. What you have on the right-hand side here is a typical corn to ethanol plant. That's a typical bioconversion process in which you're converting sugars to a fuel. Whether it is the ideal or not, but it is I guess, the perfect example to illustrate. So this process is actually very simple. Those are the reactors right there. It can operate efficiently at a small scale. You see the size of the in the picture itself, and also the barrels per day that are produced between the two of them. There's a huge difference between them. It is also low capex. Not only that per unit of output, but also overall your investment is going to be much smaller. So here is going to be in the $1 million range. In the traditional case, you're going to have, in the Fischer Tropsch case, you're going to have the $1 billion range. And this is the last point that I make there at the bottom of the slide, and there's a difference as well in terms of efficiency, overall energy efficiency, when you convert the gas to the liquid fuel. In this case, about 60%. In this case, we don't have gas to liquids, but it's, again, corn to ethanol. The energy efficiency there is higher. Now, the question is, again, this is not using natural gas. Can we leverage, can we take advantage of those specific unique features of a bioconversion to apply it to a process like this? And that is essentially where we're looking into. I guess not so fast, so we cannot make the case that today you can do that, but certainly what we have today is if you stretch your mind and you think, can I establish a bioconversion process with existing knowledge and technologies and so on, how is that going to look like? You're going to see two main barriers for a bioconversion of methane to liquid fuels, and they relate to a low overall efficiency, and you can see here it's down to 50%, and slow kinetics. Those are the two major barriers that we see, but those are the two major opportunities that we see as well to move to a completely learning curve in terms of developing new technologies. So again, that low efficiency comes from two aspects of the bioconversion process. Those relate to the activation of methane. Is that first step that you see there, the first box, it tells you how the cells get methane and activate it in a way that they can metabolize it and convert it to the fuel. So that front end only has an inefficiency that will account for a 36% drop in energy just in that portion there in that box, and you get a 22% drop in the back end as well. So these boxes actually identify two critical areas where new technologies need to be developed in such a way that you address those issues. Those areas are highlighted as well on the right-hand side, but as opportunities. And again, what you have there is efficient activation of that molecule, leveraging recent developments in the biological sciences and engineering, or coming up with completely creative new ideas. The same thing for the second box. There's a lot of improvements, a lot of different things that need to be done there. And the last aspect actually relates to this second issue here, that is the slow kinetics. A biological process is inherently slow. One side of the story is that, and you need to be able to design technologies that will be able to take care of that inherent slow kinetics. And the other one is that you're starting with the gas and you're ending up with the liquid, and the reaction is taking place in the liquid phase. So the transfer of that gas to the liquid phase is very challenging as well. Again, all of these, we see it as huge opportunities to develop transformational type of technologies that will move us from the current learning curve for these type of processes to a completely different one. So if I give you a little bit of a summary here, and again, this slide kind of highlight again what is the opportunity space here and what is the impact of a potential program or a potential set of technologies in this area. And again, we believe that if the right technologies are developed, a program like this could end up producing or developing processes for the cost-effective one-step production of liquid fuels from methane, specifically from natural gas, in such a way that that process will be having a low capex across scale. So what happens in this diagram here, you see the points are data, actual data points from a GTL Fischer Tropsch plant, and what you can see is as it goes to a lower production capacity in this axis, you're going to have a much higher capital cost, and that's what it prevents the investment in this area essentially. You multiply this number by this number, you get to the $1 billion range that I was telling you about before. We believe that technologies developed under a program like this one could actually be significantly advantageous in the sense of the capex, so 4+ reduction in the capex, if you think about that little ellipse there. And we believe that it can happen across scales. It doesn't need to be low scale, it doesn't need to be large scale, and because of that you can take advantage, that second bullet point there under opportunity, you can take advantage of any kind of natural gas resource, that being flare, remote, or that could be a pipeline gas. The impact, I guess, is easier to see for this audience. So if you are able to achieve that, essentially you'll be able to meet U.S. demand for liquid transportation fuels over the next 50 years with a domestic energy source. Because of that, you're going to reduce petroleum imports, so you're going to improve energy security. And the last bullet there tells a little bit the story of if you are able to use gas that is being burned today for nothing, like flare gas, of course you're going to reduce greenhouse gas emissions. With that, I would like to finish. This is my contact information there. What you have is my email. Then we run a workshop, as Jonathan mentioned. The output of that is posted online. And just over the weekend, we actually published a teaming list, RFI teaming list for a potential program in this area. So feel free, all of that, you go to the website, you get information there. Of course, I would be more than happy to talk to you after we finish with the presentation. Thank you.
Thank you.
Yeah, sure. Good afternoon. My name is Will Regan, and I'm an ARPA-E fellow. Okay, so we've just heard different ways to make hydrocarbon fuels more sustainable and more available. I'm going to take a different approach to the problem and consider non-hydrocarbon alternatives for which carbon and therefore carbon dioxide never even have to enter the equation. This was sort of an emerging theme from the recent Open FOA. We haven't funded too much in this area yet, but I thought it was a pretty cool area that deserves some more consideration. And I hope this talk will give you a sense of how we go about approaching and framing problems like this. So hydrocarbons have a lot going for them. They're very energy dense, both by weight and by volume, so you're not going to weigh your car down or require an enormous gas tank. So you pull oxygen, so when you combust gasoline with oxygen, you can release about 47 megajoules per kilogram, which is about 50 times what you can get in a battery of equal mass. You pull the oxygen from the atmosphere and then you exhaust your waste, so you don't reduce your energy from that, your energy density. And in addition, hydrocarbons are extremely abundant, pretty cheap, and are deployed at incredible scales. In the US, we burn about 300 billion gallons of gas a year. Some of these positives are also negatives, though. So by exhausting your waste, you're dumping CO2 into the atmosphere. And though they're plentiful now, we're actually pulling hydrocarbons out of the ground far faster than they're being replenished. ARPA-E programs like petro and electrofuels aim to solve these problems by looking at affordable ways to make hydrocarbons by pulling CO2 out of the air as fast as we're putting it back in. But there could be another solution, of course. A lot of things can burn. Can we just avoid burning something that contains carbon? So the first thing you have to ask is, can anything even come close in terms of energy density? Well, it turns out that a lot of things can. If you look at things like aluminum and ammonia, you can combust these in a similar way to hydrocarbons and release similar amounts of energy per fuel mass. Now you have to ask three things. Are these viable materials abundant enough to reach the scale of hydrocarbons? Can they burn both efficiently and cleanly? And can they be recycled both affordably and cheaply? Cleanly, excuse me. So fortunately, nature helps us out with the first problem. The lightest elements, which tend to be the most energy dense, are extremely abundant in the crust. And if you look at how fast we're pulling them out of the crust currently and processing them, they're almost at the scale of hydrocarbon consumption. You could envision potentially diverting some of these materials to the fuels market and recycling them a few times a year. Next thing you have to ask, can we burn these things efficiently and cleanly? Let's look at aluminum, which starts off with a higher heating value of about 31 megajoules per kilogram. You have a few options. You can mix it with rust, make something like thermite. That's going to burn so hot you'll probably melt your engine block. You could react it with steam in a bit cooler reactor and then get a fairly high energy density. Or you could do something at much colder temperatures in something like a primary battery or just a hydrogen source. With all these approaches, you're going to have different kinds of challenges, technical challenges, such as corrosion and adequate fill rates. And you're going to face trade-offs between something like heat management and reaction kinetics. And all of these approaches, you'll notice you've taken about an order of magnitude hit in your energy density. So this is probably going to favor approaches that generate electricity for electric motors over, which are both lighter and more efficient than internal combustion engines. Next thing you have to ask, if it's going to emit something worse than CO2, we just shouldn't bother. So say your fuel is ammonia, you want to make sure you only create nitrogen as a byproduct and not any of the nitrogen oxides. And we'll probably just want to eliminate fuels like sulfur, which will probably only produce caustic things. Okay, the last attribute, let's say it passes all the other tests. Can we recycle it affordably and cleanly? Looking at aluminum again, alumina right now requires about 50 megajoules per kilogram to be refined back to aluminum. And if you look at how much energy costs, that makes it about twice as expensive as gas as a potential fuel. Additionally, the refining alumina back to aluminum emits a ton of CO2, and it actually makes aluminum fuel more carbon intensive than gasoline, at least with current technology. ARPA-E actually is looking at this problem, or has held a workshop on the efficient and affordable reforming of metals, and a lot of these problems seem like they could be surmountable. So once again, to recap, a non-hydrocarbon alternate fuel should be both energy dense and abundant, should be capable of efficient and clean burning, and affordable and clean recycling. So thanks for your time, and I look forward to your creative ideas in the Q&A later tonight or by email. Thanks.
Well, good afternoon. My name is Rob Conrado, and I'm also an ARPA-E fellow. And as the last talk, I have an ambitious idea I'd like to share with you. To take a pointer from Hans Rosling to support the needs of the growing world's population and to supply them with renewable fuel, I keep coming back to this conflict between energy and water, this inherent trade-off between resources. And so today I have a kind of a counterintuitive talk title for you, which is, Can we engineer plants to reflect light? And I'll dig into that now. So when you look at the total water consumption for the U.S. and even for the world, you'll find that it is dominated by the water needs for irrigation. In the U.S. it's over 80%, worldwide it's over 90%. So to address this issue of available water resources, and if you want to have a high impact, you really have to address how much water is used by agriculture. But why exactly do plants consume so much water? You know, this was something I was troubled with when I first looked into it. And when you look at the water balance around a plant, less than 1% of the water consumed is actually fixed as plant matter. And so where does the rest of the water go? Well, it goes to temperature regulation. Leaves are large, they're out in the sun collecting energy, and the plants need to keep the leaves cool for biological function. And so on a really hot day, in a sunny climate, cornfields can evaporate up to 8 inches of water a month. And there are very few climates in the world with sufficient annual rainfall to support this kind of water evaporation. So why exactly do plants evaporate so much water? And it turns out that they're really inefficient. And this is an area that we've addressed with the petro and electric fuels programs and others, but I just wanted to walk you through it. If you start out with 1,000 watts per square meter, 100% of solar energy, you know, there's wavelengths that are not captured, you know, there's reflection and transmission, there's metabolic inefficiencies, and at the end you get that plants have a maximum efficiency from sunlight of about 6%. And this is a problem because all energy that is not being able to be captured must be dissipated as heat, and that ends up being a lot of water. So breaking off the biggest chunk of that, if you look at, you know, of the wavelengths not captured, looking at the total solar spectrum, plants can only use a small fraction of that as what we know as visible light. And the rest of the light, the UV, the infrared, is all heat. And that heat means water needs to be evaporated. So the question that I ask next is, well, can we engineer plants to reflect light? Not visible light, let the visible light be converted to plant biomass or fuels, but can we selectively reflect infrared light? So this is, and just to show you that this is more than just a crazy idea, nature has already evolved mechanisms for tailored light reflectance. And so I just wanted to demonstrate that this phenomenon occurs in insects, in animals, and even in plants. And so here I show a butterfly, a peacock, and a wild berry. And beyond looking at what colors they reflect, when you break it down and look at the microstructure, in several cases nature has evolved tailored organized structures to reflect light of very specific wavelengths. And what's more important is these are cellulose-based structures that plants could grow and have grown in this last case on the far right. So what if we could engineer plants and move these reflective structures from the berries but to the leaves? What kind of impact would that have? And so just to summarize, from the energy perspective, if we could engineer plants to reflect light, use less water, it would allow for a dramatic expansion of biofuels to places that currently require irrigation, but could then supply sufficient annual rainfall to support these crops. If we simply reflect all the infrared light that is not absorbed by plants, we could reduce water consumption by up to a third and address regional water scarcity. And lastly, this presents an incredible opportunity to alter the albedo of the earth and change the reflectance of the land. Since plants are so widespread, looking at just a couple key crops, you could almost completely offset the radiative forcing from greenhouse gas emissions that we currently have. So thank you for your time, and I look forward to your questions during Q&A and later today.
Those are the instructions, again. So I hope you see why it's so much fun to work at ARPA-E. These are great and stimulating technical discussions and a lot of creativity going on. I think I'd like to start out with a couple of questions. First of all, this is a technology challenge, so I'm not getting anything up here. So if you're asking questions, my apologies. Well, let me start at the discussion. Let me start with you, Ramon, because you've run a workshop. Of the technologies that you've looked at out there for biological gas to liquids conversion, what do you think is the most impactful advance that you've seen in sort of recent times?
Yeah, I think that let me turn this. And as Jonathan mentioned, we have run already a workshop, so we have received significant input from the community. There are two areas that have been highlighted as part of that process and relate primarily to the two aspects that I discussed in the presentation. So one, how to make the process more efficient in terms of activating that molecule of methane and not losing the energy that is contained in it. That could come in the form of a different mechanism that is in nature. You can think about anaerobic metabolism of methane in the seafloor, how organisms actually are able to do that in the absence of oxygen, and how that process can be harnessed and be more efficient, all the way to what I would call de novo approaches that will overcome that type of disadvantage. So I think that on the process side as well, that's what is happening. What I described before is what is happening inside the organism. But on the process side, there is a lot of challenges that have been identified and potentially new ideas that will get us into new learning curves in terms of technology development as well.
Okay, thanks, Ron. I have a question for Will, because non-carbon-based fuels is a really cool idea. But what do you think the first area where such a technology might be brought in would be for where CO2 emission is particularly dangerous?
Well, I guess you could say like batteries are a great example of essentially a non-hydrocarbon fuel. So I mean that's already gaining significant traction.
Okay.
Yeah.
And I also have a question for Rob, just to get things started. When you trade off reflected IR from plants, where does it go? Does it just go out into? I mean, it's still absorbed by the atmosphere or something like that? It's still, or is it just going to?
Well, you'd imagine that in the same way that some of the light is absorbed from the atmosphere on the way down, on the way back.
Yeah.
If it was a reflective surface, a lot of that would emit back, especially wavelengths that are absorbed by water molecules.
Yeah.
So I think a fraction would be lost, but some would be retained in the atmosphere.
Okay. So, question from the audience for Ramon, I believe. So, if you're looking at LNG versus conventional petroleum, so what are the improvements in emissions if you're going to LNG versus conventional petroleum?
You know, that's actually a very good question. So, when you think about emissions, if you capitalize on gas that is flared today, of course, I guess that it's easy to see how you are reducing emissions there, because the gas that is flared today is all converted. I shouldn't say it all. Actually, there's a significant fraction of it that goes out as methane, and the other fraction as CO2. So you save there. Based on our internal analysis, if you go beyond that and you go and capitalize on, let's say, pipeline gas, you will come even or better than what we have today for conventional oil. And just keep in mind, as we move into the next 10, 20, 30 years, we're going to be using other sources of oil that are not going to be conventional oil, and the footprint of those other sources is going to be higher than the footprint of a process like the one we're envisioning here.
Okay. I've had one question up here. So have other people texted in questions, or should we just open up the floor? Since we don't have mics, I'm sort of, this is a technology experiment. We do these a lot. So I'm just going to open it up to the floor. I'll recognize you. We have, what, about 5 minutes? Okay. We have about 5 minutes left in the session, so I'm just going to open it up to the floor, and we'll try to work out the technology issues. So.
And we have at least one microphone back there.
Yeah. Oh, so. We actually do have a mic. Okay. I'll repeat it. A question for Ramon.
Okay, thank you. Who is looking at combining thermochemical and biochemical processes rather than trying one or the other? Are there ways of doing that? Maybe breaking the methane molecule thermochemically first, something like that.
Yeah, we almost clarified, we are open to hybrid process that would be in that category there. So if a hybrid process is advantageous, we are open to that. We're not ruling that out. But the answer is no one is looking right now, very few people are looking at the biological one. That's another aspect of the approach here.
This question is for you, Jonathan. You just came through the Open FOA, which had, I believe, 4,000 concept papers, 500 full proposals, in probably about 20 or so funded aspects. So what is ARPA-E doing to mine the nuggets of technology that are embedded in failed proposals, not because the technology idea was awry, but rather maybe the team or other issues of your evaluation system were at fault? Are you passing the torch to NSF, to the DOD agencies on what those nuggets were, or is this just sort of lost time?
Well, we do that sort of data mining a lot. In fact, Will here, how long have you been with us now? You've been 4 months. Been with us for months. One of the first things he did was to go back and try to identify those things that we missed. Those technology areas that might be of interest, and that's sort of where his talk today came from. The review of both the concept papers and the full applications was a agency-wide effort. So everybody had a piece of that, right? And we really tried to condense the learnings of that into individual areas of interest that were outside the areas that we funded. So that we don't have a formal process for passing those on, but we certainly work closely with other agencies.
I would urge you to consider making that a more formal plan because obviously the other agencies are set up in a very different way, and whether they're goal-oriented or not, some are, some aren't. But you have captured so much information on what will be the drivers of technology. If that information, doesn't get transferred in a formal way, it really is a sad thing.
Understood. Thank you. Other questions?
Making a fuel as a standalone product is a tough gig, as we well know. Do you anticipate ARPA looking not only for fuel but also value-added molecules to offset, to help the revenue of a production facility? Well,
I'll field this one. I think I'm a chemist by training, so whether it's a fuel or whether it's a specialty chemical is distinguished by can you make it cheap enough to burn? If you can make it cheap enough to burn, then it's not a specialty chemical anymore; it's a fuel. So I don't really draw that distinction. I think in terms of progressing the molecules that are being made as fuel toward market, if there's an intermediate, more high-value market that can help that mature, I think that's a valuable way to go forward. But we are the Department of Energy, right? So we have to focus on that part of it.
Thanks. Clearly liquid fuel is a permanent, it's going to be a persistent problem for the Department of Defense. In particular, I mean, there are other energy strategies to other needs, right? But we're always going to need to fly helicopters. Can you talk a little bit about the collaboration or things that you've considered between ARPA-E and DoD to maybe accelerate some of the development?
I think that's a very good segue. Oops, what happened to that one? Sorry. Panel discussions this afternoon. Are there military applications in your future? Certainly, we have a very close relationship with the Department of Defense, and handing off technologies in fuels is a major area of interest for us. So, I think with that we're on time. So thank you so much for your attention. Let me go back to this slide. There's a networking reception this evening from 5:30 to 7:30. We'll all be there. These are our mugshots from the website. This is the ARPA-E technology team. Did I miss something? Yeah. Nope. And there are panel discussions that are happening, at 2:25 now? I'm at 2:20. Did I do my math right? Starting at 2:25 in these rooms. I was personally responsible for this. If you build it, will they come? Look at what drives customers. So I'd encourage you to stick around here. It's going to be a great discussion. But all of the panels this week are going to be fabulous. So thanks so much for your attention, and enjoy the rest of the summit.